Right, okay, so this is the last video probably that I'll be doing for you. So this is a commentary on the Unified paper that you took on Wednesday. It's going to be a bit of a long video because I'm going to do it all in one go. Obviously it's up to you to just to scroll through the video to the questions that you maybe want help with. Okay, so here we go. First question was asking you basically about the shape of the water molecule and hydrogen bonds. So obviously it's a question that was asked in a slightly different way to the questions on hydrogen bonding. You're asked to compare solid water and gaseous water and asked to comment on the bond angles. So you need to recognize that in a solid, the water molecule is obviously fixed in position. It's making 4 hydrogen bonds, which is going to really form that tetrahedral shape, which is the 109.5 degrees angle. Whereas in gaseous water, you've just got the water molecules individually on their own. So the lone pairs are going to have an influence on the shape. Again, still based on the tetrahedron, but because there are 2 lone pairs, each lone pair reduces the bond angle by 2.5 degrees. So you're given 2 bond angles there, 109 degrees, which will be the one that's in ice, and 105 degrees-ish in gaseous water. Why are they concerned about the release of methane into the atmosphere? It's a greenhouse gas, and that's going to contribute to global warming. And really, that's something you should know, not something I've specifically gone over with you, but you know about the greenhouse effect, you should understand about global warming. Okay, the formula of methane hydrate we're given here, and with an X for the order of crystallization. You're asked to give the formula to 2 decimal places, and a lot of you lost a mark here because you didn't give the answer to 2 decimal places. You rounded it up, which you normally would, I agree, but be careful, just read through the question, make sure you are actually doing what you need to do. So you're given the percentage up here, aren't we? 13.4% of methane hydrate is made up of methane. So we can use that value. Obviously that means the other percentage is made up of water. So we find out our number of moles, we use percentage by mass. Find the number of moles of the 2, methane and water, divide the smallest value into the bigger value, and that gives us 5.74 water molecules. Okay. And then you're asked to calculate the volume of methane in cubic decimeters. So that's important because when you use the ideal gas equation, obviously you're working in cubic meters. So if we melted a kilogram of methane hydrate, basically how much methane would be released, and you're given the pressure and you're given the temperature in Celsius. So you need to convert that. Remember, with the ideal gas equation, you're nearly always going to have to convert some units because, you know, that's an odd set of units. Okay, so we can work out number of moles of methane in 1,000 grams, which is 1 kilogram. And we can rearrange the ideal gas equation, and you actually got 1 mark for just showing that you could do that. So it's definitely worth writing something down, even if you're not sure about the calculation. So you work out the calculation, but your answer will be in meters cubed. We need to convert it to decimeters cubed because they've asked you for that. And they've asked it for you to give it to 3 significant figures. Okay, and then suggest why some industries are interested in the presence of methane hydrate. I mean, I don't know, but to me, you should know that methane is an alkane and that we use alkanes as fuels. So just because you haven't been taught something specifically in a class doesn't mean you shouldn't know the answer. You will have done it at some stage in your scientific education. Okay, question 2. So you're given quite a lot of information here to read through. You're given 3 reactions. One of them you're given an enthalpy change. Yeah. Then you're given some information about reaction 3.2 here, and you're being asked to determine the enthalpy change of 3.1. So first things first is Q equals MC delta T. So I'll move on to the next page where and this is a starred question, so it's obviously 6 marks and needs to be written in a very coherent way. Okay, so we're looking at reaction 3.2. This is the equation we're using. Now make it clear where you've got your data from. So the mass of Na2O comes from the information given to you up here. Obviously, mass of the bottle, mass of the empty bottle, do a subtraction, and so on. So we've got our mass of Na2O, 1.24 grams, and we're going to need that when we calculate delta H. We're not going to use it while we use Q equals MC delta T, but we will need the number of moles when we do delta H, so you might as well calculate them now. That's pretty straightforward, number of moles. Then you work out the mass of your solution. Now, the mass of the solution is effectively the M bit of Q equals MC delta T, because that is the surroundings. That is where your thermometer is. Remember, that's how you recognize the surroundings, the M value. You're not looking for the mass of Na2O at this point. I've written here in brackets, this is the M. So you're given the polystyrene cup, and then you're given the polystyrene cup with the solution, and again you do a subtraction to calculate M. And temperature change, pretty straightforward. Again, another subtraction, and that's your delta T. Specific heat capacity of water, 4.18. I can't actually remember if that's on your data sheet. I will double check that so that you know whether you need to know that off by heart. Okay, so to do the calculation, Q is 25.75 from here, the mass of the solution, times 4.18, the specific heat capacity of water. You're told to use that. 35-degree change in temperature, and that works out at 3,767 joules. Okay, now to work out delta H, we need to divide by our number of moles, which is 0.02. We worked that out at the beginning. Then we need to divide by 1,000 to come up with kilojoules per mole, because delta H is always in kilojoules per mole. Okay, so we've worked out now, if we go back just up here, we know the value for this equation now, the delta H for that reaction, and we're being asked to work out the delta H for 3.1. So you need to draw a Hess cycle for this. So you need to have your equation that you're looking for the enthalpy change of reaction for. So I've written up here in green, it's delta H 3.1 question mark. That's what we're looking for. Now you've done this calculation here, minus 188, yeah, for reaction 3.2. Now if you look at the I mean, this gets confusing for some students, and I understand why. So what we're trying to do here, we need to find the formation of Na2O. Right, we've got an equation here, 2NaOH is 3.2, forms Na2O plus H2O. Okay, so what I've done is reverse that equation. When it was written up here, 3.2, yeah, we want to form Na2O from this, all right, so that we can put that into our Hess cycle, that value. Now, because the equation is the opposite way round to the way it is written on above, we need to change the sign here. Yeah, so it's minus 188 is what we worked out for our delta H, but because we have reversed our reaction, we have also changed the sign, because the enthalpy change, remember, will be the same in either direction, but the sign will change. So we've reversed it. Okay, so this is enthalpy change of reaction for 3.2, because that's what we're making. Then we're given this value, the 3.3. There it is. Okay, but we're making 2 moles of sodium chloride. Okay, so from the information given, we need to multiply that value by 2. And then, of course, if you've drawn your Hess cycle correctly, you should see that you've now got 2 roots. You're going this arrow plus this arrow is going to be equal to this arrow. So I've had to write it up here because it kind of ran out of space. Not ideal when you're trying to write something really clearly for an examiner. So we've got plus 188, yeah, here, plus our delta H 3.1 is equal to 2 times minus 57.6. And when we rearrange that, obviously we get our delta H for 3.1 is equal to minus 115.20, which is 2 times that, minus 188, because we've taken it over to the other side, and there's your answer, minus 303.2 kilojoules per mole. Okay, so if you want the 6 marks, you need to do it in that kind of methodical way. Okay. And then you're asked to calculate uncertainty. You're told the uncertainty in the temperature reading is plus or minus 0.1, and the uncertainty in the mass reading is plus or minus 0.005, and asked to determine whether the mass of Na2O or the temperature change has the greater percentage uncertainty. Straightforward calculation. You take your uncertainty value, whatever you're given, and you divide by whatever it was you measured. So in our case it was 35 degrees and 1.24 in terms of the mass. Divide that into your uncertainty value, times it by 100, which gives you a percentage. But because you took 2 readings to get the temperature value, you took a beginning value and an ending value, you've got to multiply your answer by 2. And the same for the mass. You took an initial mass of the or whatever it was we weighed it out in, weighing bottle, and then you re-weighed it again. So again, you need to multiply by 2, and that gives us a greater uncertainty with the mass. Suggest a modification using the same apparatus, so not asking you to come up with a different method, it's just asking you how you might reduce a percentage error. Well, if you think of that equation to calculate percentage error, so your uncertainty over the mass measured times 100, if you increase the mass, you're going to make your uncertainty and you're dividing it into the same value for the uncertainty, you're going to end up with a smaller number. Okay, so if you have a greater mass that you weigh out, you will reduce the uncertainty. And that applies, in lots of instances. For, if you're asked that kind of a question, you apply the same logic to it. Okay, we're told that Na2O can be prepared using a redox reaction of sodium metal. NaNO2 and sodium metal, will form Na2O, okay, plus nitrogen gas. So I just scribbled down, didn't bother to balance that, I just wrote it down just to kind of remind myself what was actually changing here. The systematic name for NaNO2 is going to be sodium nitrate 3, because it gives the oxidation state of nitrogen. That's what that Roman numeral 3 is telling us, that this has an oxidation state of +3, nitrogen in this case. You could, if you wrote sodium nitrite, you were given that you were given the mark. But technically, the proper name is sodium nitrate 3. And then you're asked to work out which oxidation numbers have changed, and that's why I wrote that equation there, scribbled it down. We can see that sodium's gone from 0 to +1, and nitrogen's gone from +3 to 0. And then you had to balance the equation. Okay, so that's pretty straightforward, I hope. Question 3. Okay, so this one is about rates of reaction. You're asked to write a rate equation and calculate the rate constant. So this is quite a straightforward one, to be honest. As you look at these different reactants, as you double the concentration, keep the others the same. On this side you can see that the concentration, the rate doubles, so that means we're H2O2, it's to the order 1. Same for I minus. Okay, so we have a rate equation written like that, and then we can work out, we're asked to calculate K, which is pretty straightforward. Just plugging in numbers from the table. I just picked the first line. I think I said, oh yeah, this is a number of you keep missing this. This is the rate is whatever it is, 2 times 10 to the minus 6. So obviously that makes a big difference to your calculated answer. Make sure you look in the table to see the full units and the values. Okay. Yeah, so to work out the value 0.01, so I took the values from here, and 2 times 10 to the minus 6 from here, and then the units, of course, I just wrote them out, cancel out what I can. I have to bring this one up, so I put in my reciprocal value, so moles to the minus 1, dm to the 3, seconds to the minus 1, because that's staying on the top. Straightforward, really, for 3 marks. You need to really know the Arrhenius equation and what you can do with it, how you can manipulate it to find different values. You're asked how you'd be able to find activation energy, and if you plot log K against 1 over time, 1 over temperature, measure the gradient, and then the activation energy is given by the gas constant minus gas constant times the gradient. Okay, so we're looking here at electrode potentials. We were told that hydrogen peroxide decomposes slowly, but if we add the catalyst manganese dioxide, the reaction happens faster, and it's basically asking you how we can show that by using this information here. So you know you're going to have to use this information. So we are looking at, we know what a catalyst is, we know that a catalyst is something that is regenerated, so we're hoping that our MnO2 is going to end up at the end as being regenerated. So if we look at hydrogen peroxide and manganese dioxide, add those 2 equations together, yeah, cancel out what is common, and then come up with your final equation there. We've got hydrogen peroxide, manganese dioxide, and then we've got manganese that has been so we've got our manganese that's been reduced here to manganese 2 plus. So then if we add the equations of hydrogen peroxide and manganese 2 plus together, oh, bear in mind, yeah, we need to reverse the whichever the value is the more negative. Don't forget, so in this case, then the first reaction, H2O2 is on the left here, and whereas on the right up here. Yeah, so we've changed it over. Yeah, and we've got to do the same, obviously, down here. You take the more negative one, which is this one, and swap it around. So we've got Mn2 plus 2H2O, etc. Again, we cancel it out, and we end up with our MnO2 being regenerated, which is what we were hoping for. Yeah, don't forget that about reversing the equation. Yeah, you know, you have to work out which one is being reduced and which one is being oxidized from the electrode potentials. Take the more negative one and swap it around, basically. Okay, of course you won't have heard probably of this kind of substance, peroxycarboxylic acids, you know, but that doesn't mean that you can't work out, if you understand the chemistry behind their reactions of different, you know, carboxylic acids, that you won't be able to work something out just because you've never heard of it before. So it asks you to suggest a structure, and this is the structure. basically, but you did get the mark if you put the oxygen on the other side. And then you're told that there's an equilibrium and you're given an equilibrium constant, and given some information about concentrations of different substances, and then you're asked to calculate in moles. So that's basically not concentration. Okay, so it's easy to kind of stop halfway through the calculation, forget that you've actually got to go that step further and calculate moles from concentration. So if you write the equilibrium expression, which is pretty straightforward from here, sorry. Yeah, write the equilibrium expression, do the calculation, you work out the concentration of your peroxy ethanoic acid, and then from that we work out our number of moles. Yeah. Number of moles, concentration times volume. Now this seemed to cause a few problems, and so it's very important that you are aware of how you read a burette, and also how you calculate the average titer. So you're given 3 different titration readings here. You're asked to take the reading from the burette, and a number of you didn't quite get it right. So you're looking at the burette, you're looking at the meniscus, where is it sitting? Yeah. And obviously in this particular case here it goes, what 0.1, 2, 3, 4, 5, 6, so it's 0.6. You always write values from a burette, you always write them to 2 decimal places, so it's either going to be 0.6 or 0.60 or 0.65, depending where the reading. So your initial reading is 0.60, and in this particular titration the final reading is 23.15, because the meniscus is between the 2 gradations on the burette, so it's 23.15. Okay, so then you do a subtraction, you do the same for all 3 of them, do a subtraction, but you only use concordant results, so results that are within 0.1 cubic centimetre of each other. So you shouldn't have used all 3 values to get your mean titer. So your mean titer here is 22.5. Right, okay, so we are told that compound A looks like this, and it's got an R group on the side, and we don't know what the R group is. It's also told that it has 4 optical isomers, so it must have 2 chiral carbons. Yeah. Okay, use the information and the results, students' results, so you're going to have to use this value here somewhere. Okay. We're asked to determine the molar mass of A, and then hence the formula of the alkyl compound, and then to draw the compound and label any chiral carbons. Okay, and we know that there must be 2 of them, otherwise we wouldn't have 4 optical isomers. They're told it's monobasic, so that means it's a 1-to-1 ratio with NaOH. So if you can work out your moles of sodium hydroxide, you know your moles of acid. So we take our titer, we multiply it by the value that we're given up here somewhere. Here we are. Here's our concentration of our sodium hydroxide. Yeah. So concentration of sodium hydroxide times the volume, and we work out the moles, and that's in 25 cubic centimetres. So we've also got that number of moles of compound A in there. Now, we're told at the beginning in the question again that it was in 250 cubic centimetres. So we need to multiply that up by 10. We've actually got 1.89 times 10 to the minus 2 moles of compound A. Okay, we can work out the molar mass of that because we were told the original mass, and now we know the number of moles. It's 132 grams per mole. So that means we can subtract the rest of the molecule. If we work out the molar mass of the rest of the molecule, we can take that away from the total, and that gives us the R group, which is 57, molar mass of 57, which converts to C4H9. And really, because you need 2 chiral carbons, there are a few different structures you could have drawn, but you've got to bear in mind that you need 2 chiral carbons. Okay, so there's your structure. You did get a mark if you drew a different structure, but it was technically correct, but it didn't have 2 chiral carbons, so you would have just lost a mark for that. Okay, so compound A again, and then it says that we carry out 2 reactions using this compound, but we don't need to worry about R, we're just using it as an acid. Okay, so you're told that magnesium ribbon is added to it, and gas bubbles are seen. So you're asked to write an equation. Well, it's an acid plus a metal, you're going to get a salt plus hydrogen. So basically you've got to balance that out, and it's a redox reaction. Okay, this one, yeah, I'm not sure that anyone got it right, because you wouldn't necessarily know what a dimer is. It's not a term that you may be familiar with, and it's certainly not a term that is in your specification, but you will know now, obviously. I've written down here the definition. It's a molecule formed by a combination of 2 smaller identical molecules. Okay, so you're told it's heated with concentrated sulfuric acid acting as a catalyst. So we've got 2 molecules of A, and they're both going to lose water, yeah, from the alcohol group, and the H from the acid group. So it's going to be a condensation reaction, and this will be your dimer. If you look at it, it's really the only way that it could be joined together if you've lost 2 water molecules. Okay. Yeah, this one, probably put you off when you first saw it, but it's actually a very straightforward. It's just a transition metal compound, isn't it, with a bidentate ligand attached to it. So 3 bidentate ligands. Okay. They've asked you to draw it out, and some of you missed off the minus on the oxygen, which needs to be there for that mark. Tablet of chromium picolinate contains 200 micrograms of chromium, and they tell you that 1 microgram is 10 to the minus 6 grams. Okay, and asked to calculate the mass in grams of chromium 3 picolinate in a typical tablet. Okay, so we work out our moles of chromium because we're told how many grams we've got. We can look up the mass of chromium, the atomic mass rather of chromium. There we are. There's our number of moles. You can work out the molar mass of this compound. Yeah, it looks a bit tortuous, but it's not actually that bad. If you work out the molar mass of one of the ligands and multiply that by 3, and then add the atomic mass of chromium to it, it's 418. So once we've got our moles and our molar mass, we can work out what the mass of this substance in this tablet is. Okay, pretty straightforward. Moles times molar mass. Don't be put off just because it's an unusual looking molecule. All right. This goes for this as well, really. I mean, this is you won't have come across maybe butane 1-thiol, but you're told that it has a functional group of SH and basically forms thioesters. So, it's a weak acid. So if it's a weak acid, it loses the hydrogen. So it's straightforward enough to write the expression for the acid dissociation constant. If you're not sure, just write out the equilibrium first and then put it into the expression for Ka. And it says that they react with carboxylic acids to form thioesters. Yeah, so it's going to form the equivalent of an ester group, but with a sulfur rather than an oxygen. And you're very familiar with esters and formation of esters with alcohols and acids. So it's the same idea. So if you draw out the structure of the molecules, you can see where the water is lost, and then they're just going to join at that point, as they would if it was oxygen here. You wouldn't think anything of it, but because it's sulfur, it seems to have thrown a few of you. Okay. And then you're asked to draw the skeletal formula for 3-methyl-butyene-1-thiol. Now, when I was doing this, I thought, well, I just scribbled it out in a kind of half displayed form, just to give me an idea before I tried to draw the skeletal formula. And then, because once you've got that there, it's pretty straightforward. But just remember to cross it out to show that you don't want it that bit marked. Okay, propane 1,3-dithiol reacts with carbonyl compounds in condensation reaction to form a cyclic organic sulfur product. Now, I agree this is a little bit, you know, daunting maybe to think about how this comes together, but actually it's pretty straightforward. I mean, I just scribbled this out to kind of work my way through it. So I've got the two structures here. I've got the dithiol and the ketone. We know we've lost water, so we must have lost the 2 hydrogens and the oxygen. So basically then we've got to find a way of putting all this together in a cyclic way, okay? And I sort of drew it out like that. But you need to draw the whole equation. Now I've actually missed off the hydrogen. I should have hydrogen here, SH and SH. Don't forget. I left it off because I was thinking skeletal formula, but that's a mistake. You should have SH and SH. So the 2 H's and the O have gone. Don't forget to put your H2O. And then really there's no other way. This carbon here just comes in and joins, you know, these bonds to these 2 sulfurs, and then the other 2 carbons are left kind of trailing. Okay, so this is the last question, and this is another starred question. Yeah, so you're given all these different organic structures, okay, and then you are asked, you're told, that here we are, explain how chemical tests would allow each compound to be distinguished from the other compounds. In your answer, include essential details for all test procedures and observations. You are not required to give details of apparatus and quantities. So they don't want you talking about, you know, condensers and stuff like that. All right. What they want to do, what they want to know is, do you know how would you distinguish these 6 compounds from each other by following us, you know, working out a series of tests. So I've written here, first thing is to do is identify the functional groups in each compound, which I've written under each one. And then think about the order that you will test for them so that you can use the minimum number of steps to identify each one by a process of elimination. If you don't plan this answer, it's going to be really hard to achieve full marks because, you know, it just becomes all messy. So scribble on the back of the exam paper, have some kind of plan in your head before you start writing the answer out clearly. Now I've done it in the way that I think I would do it. There's lots of alkenes there, so the first thing I would do is establish which ones have got alkene group in them by adding bromine water. And then there are a number of compounds that if you added acidified dichromate to them, they should go from orange to green, so it kind of indicates to you that you've got an alcohol or a ketone or something present. 2,4-dinitrophenylhydrazine, again, will tell you that the carbonyl compound is present. So C, E, and G. So yeah, so we've got the aldehyde, the ketone, and the ketone. We've got 2 ketones, haven't we? So we'll get an orange precipitate, and then we need to establish which one is the aldehyde, which one's the ketones, and then if we add Tollens reagent, we'll get a silver mirror. So you've kind of got information here now that should enable you, by process of elimination, to work out which one is which. Yeah, the most obvious one is C, because that's cropped up a few times. That is an aldehyde and an alkene. Yeah, because it responded to bromine and it responded to 2,4-DMP, so that must be the citral, yeah? And so on, really. Then you start to establish, okay, what else have we got? We've got D and D here. So it turned the acidified dichromate green, so it could be a primary alcohol and an alkene. Yeah. We also got a positive response for C from 2,4-DMP, which shows there's a carbonyl compound there. So there's the aldehyde aspect of it, and also it responded to Tollen's reagent, didn't it? So we know it's an aldehyde, yeah, with the silver mirror. We know it's an alkene, so you know the aldehyde and alkene that is there is citral. And so on, really. You go through each one and eliminate them via different tests, yeah, which will tell you individually which ones they are. So I've got here B and E only responded to one test, yeah, so which means they only had one functional group that was reacting. B is a tertiary alcohol, so that's not going to react to H plus Cr2. So we can assume that B was linalool, what that is, and E is the ketone on its own, which responded to 2,4-DMP. Yeah? So you can see that by process of elimination you can work out those 6 compounds from those different tests, but you've got to be methodical in the way that you write it down, how you're going to approach the test, and how you're then going to show that you've identified them. Okay, right, that was a bit of a marathon, nearly 40-minute video, but you don't have to watch it all, obviously. You just find the questions that are actually relevant to you. Okay, and as I say, that will be the last video you have to watch from me. Okay, bye.